As concern grows among scientists and astronomy enthusiasts about a potential interaction between Pluto and Neptune, prominent experts like Neil deGrasse Tyson and Michio Kaku have raised serious questions about what such a cosmic event could entail. But how did Pluto end up on an orbit that might intersect Neptune's, and what would the consequences of such an encounter mean for Earth? Once considered a full-fledged planet, Pluto was reclassified as a dwarf planet due to its highly eccentric orbit. Despite this redefinition, its mysterious path continues to fascinate astronomers. Recent studies by leading academics have drawn attention to the increasingly close proximity of Pluto's and Neptune's orbits, even warning about the remote possibility of a future collision, a scenario that could have implications extending even to our planet. Pluto's orbit is among the most unusual in the solar system. It takes roughly 248 Earth years to complete one revolution around the Sun, and since its discovery in 1930, it hasn't yet made a full orbit. Its path is highly elliptical and inclined at about 17 degrees relative to the ecliptic plane, making it stand out from the near-circular orbits of the main planets. At certain points in its orbit, Pluto actually travels closer to the Sun than Neptune, something that seems alarming at first glance. So, why haven't the two collided? The answer lies in the complex gravitational interplay between Pluto, Neptune, and the Sun. This intricate relationship is an example of the three-body problem in orbital mechanics, which explores how the gravitational influence of three massive objects affects their motion over time. Key concepts like asynchronous libration, nodal libration, and the VZK von Zeipel-Kozai oscillation explain how Pluto's orbit, while chaotic in appearance, maintains long-term stability. Asynchronous libration ensures that when Pluto's path intersects Neptune's orbit, the two are never in the same place at the same time, remaining offset by at least 90 degrees. Nodal libration adds another safeguard, keeping Pluto either well above or below Neptune's orbital plane during near crossings. The VZK oscillation accounts for Pluto's seemingly erratic but stable orbital behavior across immense time spans. Simulations dating back to the late 1980s demonstrated Pluto's orbit to be chaotic. Small changes in its initial position or velocity could lead to vastly different paths over millions of years. Still, these same simulations confirm that Pluto's current trajectory is remarkably stable on billion-year timescales. Advanced computer models have deepened our understanding of how giant planets, especially Jupiter, Saturn, and Neptune, shape Pluto's journey. A key element is the 2:3 orbital resonance between Pluto and Neptune. For every 2 orbits Pluto completes, Neptune completes 3. This synchrony adds an additional layer of protection. Jupiter's massive gravitational pull also plays a stabilizing role, while Saturn contributes to this delicate celestial balance. These gravitational mechanisms are essential to maintaining the solar system's orderly structure. Without them, the solar system could become increasingly chaotic, raising the likelihood of collisions or the ejection of objects from their stable orbits, with ripple effects throughout. Understanding Pluto's orbital characteristics is especially important in light of ongoing concerns about a potential collision with Neptune. While the risk is exceedingly low, studying Pluto offers deeper insights into how the solar system maintains its delicate equilibrium. It also illustrates how orbits that appear unstable on the surface can be stabilized through gravitational harmonics and resonance. Continual observation and simulation are vital for refining our knowledge of these complex dynamics. Pluto's behavior showcases how even small changes in celestial bodies' velocity or position can radically alter its long-term path. Yet, paradoxically, its orbit still exhibits a deep-seated order. Sophisticated simulations help scientists estimate future trajectories, but their accuracy hinges on precise initial data. Even a tiny miscalculation can result in wildly different forecasts. This unpredictability reminds us of how little we still truly know about the cosmos. Although direct planetary collisions are rare due to the vast distances and stabilizing forces at play, concerns persist. Rogue planets are uncommon compared to stars and stable planetary systems, yet gravitational chaos remains a persistent possibility in celestial mechanics. Some scientists continue to express concern about a hypothetical Pluto-Neptune impact. Why? Given all the stabilizing factors, do these warnings still gain attention? Neil deGrasse Tyson, a leading astrophysicist, provides valuable perspective. Known for advocating Pluto's reclassification as a dwarf planet, Tyson doesn't see the change as a demotion, but as a natural evolution in our understanding of the universe. He views Pluto's eccentric orbit as a symbol of how much remains to be discovered and stresses the importance of continued education and adaptability in astronomy. In his view, Pluto's orbital quirks are not just anomalies, they're reminders of how dynamic and mysterious our solar system really is. Exploring these mysteries not only enriches our understanding of celestial mechanics, but also fuels a curiosity that drives science forward. The intrigue of cosmic exploration is something Neil deGrasse Tyson finds deeply compelling. He emphasizes how high-profile celestial events, such as Pluto's orbital anomalies and its reclassification from planet to dwarf planet, can spark public curiosity and deepen interest in astronomy. By spotlighting the dramatic and sometimes bizarre nature of orbital mechanics, Tyson aims to make space science more accessible and inspiring beyond academic circles. Tyson has also raised concerns about the potential dangers linked to Pluto's erratic path. Drawing on extensive research, he warns that the three-body problem, a complex gravitational interplay involving Pluto, Neptune, and the Sun, could pose real threats. He suggests the possibility of a long-overdue collision between Pluto and Neptune, which could disrupt the delicate gravitational balance of the solar system. Such an impact would be unprecedented, possibly shattering Pluto due to its icy composition and releasing massive debris that could endanger other planets and moons. Neptune, depending on the collision's dynamics, might experience shifts in its orbit or atmospheric conditions. Michio Kaku, a renowned theoretical physicist and expert in string theory, also weighs in on the implications of Pluto's orbit. He views its unpredictable motion as a gateway to deeper understanding, not only of planetary dynamics, but of fundamental physics itself. Kaku believes studying gravitational interactions, especially between bodies like Pluto and Neptune, is essential for future space missions and navigating the outer solar system. These insights could help scientists better prepare for unforeseen cosmic events. Kaku frequently highlights how orbital mechanics are tied to the foundational laws of physics. The complex dance between Pluto and Neptune, he argues, illustrates the universe's hidden structure. His work in string theory, a framework that seeks to unify all forces and matter through vibrating strings, may gain critical insights from such celestial events. A Pluto-Neptune collision could generate extreme gravitational forces and energy, offering a rare chance to test string theory predictions in real conditions. The gravitational waves produced could provide data on space-time behavior under intense conditions. While Earth would likely be physically unaffected due to the vast distance from such a collision, the scientific impact could be profound. It might transform our understanding of matter, gravity, and the universe's deeper mechanics. Pluto's orbit exemplifies the dual nature of stability and chaos in our solar system, shaped by the gravitational tug of massive neighbors like Neptune. Though the chance of planetary collisions remains low, they are not outside the realm of possibility, reminding scientists that our cosmic neighborhood still holds many unpredictable and potentially hazardous mysteries. Gravitational forces, especially in complex systems, are exemplified by the three-body problem, most notably in tightly packed systems like TRAPPIST-1, which contains 7 Earth-sized planets. In such environments, gravitational interactions can lead to rhythmic orbital resonances. Over time, these resonances have the potential to destabilize planetary orbits, increasing the risk of collisions. While TRAPPIST-1 currently appears stable, astronomers closely monitor its planets to better understand how tightly grouped celestial bodies behave under gravitational stress. This research offers crucial insights into the broader dynamics of orbital evolution. Adding to the cosmic complexity are rogue planets, planetary bodies that drift through space after being ejected from their home star systems due to gravitational disruptions or interactions with nearby stars. These wandering planets can travel vast distances across interstellar space, potentially venturing into regions far from where they originated. Although the vastness of space makes it highly unlikely, there's a slim chance that a rogue planet could pass through another star system and even collide with one of its planets. However, the probability of such a direct impact remains extremely low due to the sheer emptiness between stars.